Hello, I'm Ankur and this is Abinash, and we will be talking about probabilistic graphical models using pgmpy. So starting with a basic introduction to PGMs. Probabilistic graphical models are basically a technique for representing joint probability distributions over a set of random variables in a compact way. And it also provides us techniques for doing inference over it in computationally efficient ways. So basically, we exploit the independence condition between the random variables to have a graph structure representing the relationship between the variables, and we have some parameters over this graph which we can combine over to get the final joint probability distribution. So mainly there are two types of graphical models. One is the Bayesian model and the second is Markov model. Bayesian model consists of a cyclic directed graph, and we use it whenever we have kind of a causal relationship between the variables. Markov model is kind of undirected graph and is parameterized using factors, and whenever there is non-causal or there's kind of like we want to know the agreement between the variables, we use Markov models in those cases. So yeah. So we can take a simple example of a Bayesian network of a student taking a course at university. So here we are representing the course by 5 different variables: the difficulty of the course, the intelligence of the student, the grade that he gets in the course, the recommendation letter that he gets from the professor, and his SAT score. So we can see here like the grade that he gets depends on the difficulty of the course and the intelligence of the student. And based on the grade, he gets a recommendation letter, and his SAT score depends on the intelligence. And corresponding to each of the random variable, we can see that we have a conditional distribution table associated with it. And with each variable, it represents the probability of that variable given its parents. So basically, D doesn't have any parents, so it represents simply the probability of D. So getting for the difficulty of the course to be easy, let's say we represent it by D0, the probability is 0.6, and for it to be hard is 0.4. And similarly, we have defined CPDs over all the variables. So this is how we parameterize a Bayesian model. And now coming to creating similar like this model using pgmpy. So basically, first two statements are the import. We import the Bayesian model class and the tabular CPD. Then we define the student model network. So there were 4 edges in the network, if you can see, like difficulty to grade, intelligence to grade, grade to letter, intelligence to stat. So we have these 4 edges in defining the student model, and then we define the CPDs over each of the variable, and these CPDs are tabular CPDs. pgmpy supports other CPDs also, like tree CPD or rule CPD. And we can see like for every tabular CPD, we in general need 5 arguments: the variable name, the cardinality of the variable, that is the number of states that it can take, the values corresponding to each of these combination of states of parent and the variable, the evidence, which is basically the parents, and the cardinality of the parents. So this is how we define. And then for associating these CPDs with the network structure, we can simply call add CPDs method and pass it all the tabular CPDs, and so we can like have a complete representation of our Bayesian model. After creating this model, we can simply do some queries like nodes. It will return all the random variables in the network. Do edges or do get CPDs. It will return all the CPDs over associated with the network. Or we can print it like this. It will show it in a tabular form. Coming to so as I told, like the network structure of the Bayesian model stores the independencies between the various random variables. So like there are multiple types of independencies in the case of Bayesian model. One is the local independencies, which says like a variable would be independent of all its non-descendants given its parents. So for, let's say here the G variable, it's independent of S given D and I. So coming back to the model, we have the parents were D and I, its descendant was L. So given D and I, it will be independent of S. So pgmpy supports many of such methods which do simple queries over the network. Then there's active trail, which basically defines like whenever there is dependence between any two variables in the network, so they are said to be on an active trail. You can even query those using pgmpy. Simply do active trail nodes, the observed variables. It will return a set of variables which will be affected by changing the variable that we had provided. So in the previous example, we had considered that we already have all the parameters of the network, but in real life, we don't have those parameters, and generally we have the data. So pgmpy also supports parameter learning, which can directly learn from the data given the structure. So here we have created some random data using NumPy, and have created a data frame object using it. And we created the student model, the structure of the network, and simply did a fit over the trained data, and we can get all the CPDs that have been learned from the data. So the current implementation uses maximum likelihood estimator to learn the probabilities, the tabular CPDs, and we are still working on the Bayesian learning part, and we can see like the learned CPDs. Okay, so coming on to inference, Abinash will be taking over from here.
Okay. In the previous section, we saw that, okay, once you learn the parameters and how to learn, in the previous section, we saw how to learn the parameters, and if you know the parameters, how to add into the model itself. In this section, we will be basically seeing, okay, how to do any kind of inference when you have learned the parameters itself. So in pgmpy, basically to learn to do inference, you have the inferences classes. So currently, I would be showing only the example of a variable elimination method. So to create an inference class, basically you need to instantiate with a model that you want to run. And to infer from this, the API is simple, it is the query method. So you just call the query, it will give you it will provide you a dictionary consisting of the query variable and the factor formed from it. So for example, now we did the inference on the query of the D variable. So it basically gives us a dictionary, and I'm printing the D variable. So apart from that, it also supports, okay, you can also run this inference when you have the evidence as well. For example, in this case, if I know that the student has intelligence and the grade is very low and the letter of recommendation is good and other parameters, so I can basically give this as an inference, as the evidence. So it will also run the inference query and will give you the results back. So inference objects also supports the map queries. By using the map query, you can find the most probable state that you would be having, that you would be getting. For example, if you want to run which is the most probable state of the difficulty of the subject, you can get it through the query. And it also supports the evidence part as well. So if you know that, okay, the student has the, you know the intelligence, the grade and everything, you can provide this as the map query and it will also run for you. So apart from that, if you don't want to create any variable, if you don't want to create an inference object class, it has also a predict method that is similar to that is present in the scikit-learn. So basically, you can also predict using the test data. So as you can see over here in the test data, we basically drop the grade table, and you want to predict, okay, what is the grade of the student given all the other variables. So it is able to predict. You can just run the predict method. So this is only one of the example that I shown using the variable elimination. We have also the methods to create the junction tree, belief propagation algorithm as well. For example, this is how you can create using the belief propagation algorithm. This is similar to the ones that you saw in the variable elimination. Okay, one of the major advantage of using pgmpy over any other library for probabilistic graphical model is that pgmpy has very easy extensibility. So you can add your new inference algorithms very easily to pgmpy. For example, if you want to create an inference algorithm that will randomly pick up any variable factor associated with the variable, and it will reduce all the other variables that are present in this factor, and it will return you the factor itself. So this you can do it very easily. So you can create another my inference algorithm class that basically inherits from our base class for doing inference, and you can create your own query method. So using this gives you more flexibility to write your own inference algorithms which is not present in any other library. So apart from that, the pgmpy also supports reading from various file formats for graphical models such as XML Vif, XML Belief Network, and the various other file formats. In this, I would be basically showing you an XML Vif file format. So basically, this is a file that basically contains all the variables. So to read this file, it is very simple in pgmpy. You basically create a XML Vif reader, instantiate with a file name, and you just call the get model. So once you call these methods, it will basically give you a model, and you can just check the model.nodes. Model.getCPDs will return you all the CPDs. And okay, these are the features that are going to come in the pgmpy. So one of the major features that you are currently lacking is the structured learning. And now we are also going to introduce the dynamic Bayesian networks, sampling methods, and approximate inference algorithms. So that's all that I have to show.
Questions for either our speakers? You had an image of one of the networks visually.
Yeah.
Is there a method generated?
Basically, all the graphs that you are seeing in pgmpy are the network X graph. So you can plot them using the matplot network X plotting features.
All right, let's just thank all of our speakers and for a great session.